Yes, you have a question?
So, this might be a stupid question, but when we were working with the current and voltage for resistors and capacitors,
Right.
we said current R or current C. So, are we talking about like an AC circuit that has a capacitor on it and an AC circuit that has a resistor on it?
As opposed to an
As
AC
opposed-
circuit that has both?
Or no, as opposed to like the resistor, its current?
Run your question by again.
So the AC that the thing set up AC capacitor.
Right.
That's what we're looking at and we're looking at the current through that.
Right.
That's what we're doing.
Yes.
And then it's the same thing just for the resistor.
Right.
We're looking at the current through that.
Yes.
I just
And-
double checking because like I was looking at my notes and I put IR in phase with VR and I'm like, okay, what? And this was 2 nights ago when my sleep schedule wasn't fixed. Actually, I think that was its worst. That was 6 a.m.
Okay. 6 a.m., good time to study physics.
But
Yeah, I'm not quite sure another interpretation, that's the part that's messing me up. Because if I have a resistor and a capacitor in the circuit, it's still the same thing. IR is the current going through the resistor and IC is the current going through the capacitor.
yeah, I think I was thinking that the current was coming from the capacitor, or from the resistor.
Well, in a sense, yes, but
Not in the way I'm.
because we've only done the series circuit, right? We haven't done the parallel.
Yeah, I'm pretty sure. Yeah, yes.
But the series circuit, the current flowing on and off the capacitor is the same current flowing across the resistor, which is the same current coming out of the power supply.
Okay. Okay, got it.
All right. Other questions? I'm assuming Micah speaks for everyone then. All right, excellent. Congratulations. Ah, it did finally go away. Okay.
That looks like a little dude.
All right, so let's take a look at the parallel circuit, the RC parallel, the AC RC parallel. I just can check that. All right, obviously R, C. We have a power supply here. So let's assume that, no, let's take it one step back. Frequency is 50 hertz. At time, at t equals 0 seconds, epsilon sub naught, or which is the voltage from the power supply, is equal to its amplitude. So to refresh your memories from so long ago, I knew the voltage coming across the power supply is equal to some amplitude, because again, we have this sine or cosine function oscillating back and forth, times the cosine of omega t plus phi. And by saying that time is equal to 0, I'm at the peak. Well, we can just sort of work through that. So with cosine of phi, because when time is 0, the first term is 0. So the cosine of phi is equal to 1, or phi would be equal to 0. And as is convention, I did not put units down, so it's understood to be radians. Should be understood to be radians. So right off the bat, we know that the phasor that's zipping around the central point is being described by, let's see, for the voltage for the power supply, it's equal to epsilon naught cosine of omega t. So we've, first bit of information just tells us that there's no phase shift there. All right, omega, that's the next bit of information here. How do we find the angular frequency? If you are given the frequency.
Was it the 2 pi something?
2 pi frequency.
2 pi, yeah.
All right, so it's equal to 2 pi times the frequency. So 2 pi times 50 hertz. And that equals 314 point, let's see, 3.14159. That's as far as I can do in my head.
314.1592. I mean, it's gonna wrap off, so.
Units.
Radians per second.
So we can now take our voltage supply, and we now have an exact equation for it. That the voltage from the power supply equals epsilon sub naught cosine of 314.1592 radians per second times time.
And we know what epsilon sub naught is, right?
I didn't give it to you.
Oh, is that not the value that we were given in the previous chapters?
Well, it could vary depending upon the problem.
What would we usually be given?
Oh, you're talking about the permittivity of free space?
Yes.
No, it is a completely different one.
Obviously.
Okay.
Again, we've run out of letters. We have 100 to work with.
So this epsilon sub naught is
EMF, it's the
the voltage.
maximum voltage.
Max, okay. I was running under the assumptions of the letter.
Do I need to come out with a video of do not confuse these epsilons?
Yes.
Okay. There's as many epsilons as there are mu's. All right, so let's figure out what we do know here. I've got 3 components. Each one will have a current phasor and a voltage phasor. So that means I have 6 phasors to put down in my phasor diagram. And so, well, let's just, what's actually, when you're ever doing the phasor diagram, my recommendation is to pick the one that is going to be that's most common. So what's common to all 3 things in parallel?
Wait. It's not it's the voltage? No. Yes. No.
The current.
Current. No, current. Ammeter is your voltage.
The current.
You're going with current, you're going with voltage. And fight. All right, do we have a tiebreaker?
Voltage.
Yeah, it's voltage. Because whatever path I take, I need to add it, yes, end up at 0, Kirchhoff's voltage rule. So whatever I gain here, I'm going to lose across there, so my voltage difference has to be the same. And same here as well. Also, current can't have a junction where it could split, so any current that flows across here is going to split between these 2. So I've got So I'm just gonna stick, once its voltage is the same, that's equal to V sub R, which is equal to V sub C. So that's three phasors right there, all smack dab on top of each other, because they're equal.
Now, all phasors are just current and voltage, or the things that go on a phasor?
The only ones I've ever seen in a phasor diagram are currents and voltages. I guess you could have a charge phasor.
But very not common.
Yeah, I'm trying to think if no, I don't think I've ever seen that. All right, so, current phasor.
Eli the Iceman. What was the L in Eli?
Inductors. So we have there's no inductor in here, so we don't have to worry about Eli, just the ice.
Oh, wow. For the capacitors, or for the capacitor, the current will lead.
By how much?
90 years.
Okay. So if it leads, because again, these things are going around counterclockwise, so it's sort of, that's supposed to be a 90-degree angle, or pi over 2. That is the current from the going across the capacitor. All right, 2 current phasors to go. We should do resistance next. Sorry.
Would the current, I think I was remembering this right, from the power supply be right in between? Or is that the wrong, is it not the wrong?
It will end up being, because if you think about this like a DC circuit, if I have current flowing this way, it's going to split. So whatever current's flowing across here plus the current flowing across here would have to add up to the current coming out of the power supply.
Mhm.
So it will end up being, in terms of phasors, in between, because I have to add.
Is that one of the 6 that we were thinking of, or is that another one?
No, that is one of the 6, but we need to do resistance next. So what do you know about the phasors of the voltage and current phasors across the resistor?
Well, it's supposed to be before the capacitor. The current for the capacitor. Right? Because that leads. But.
So it'd be, would it be the point like right below the epsilon sub-zero? Like,
You're talking about the projection on the horizontal axis?
yeah.
That's the instantaneous value. What do you know about the phase difference between the current and voltage phasors of a resistor?
Current and voltage phase. The voltage phase, the voltage for the resistor. Never mind, we already got that one.
Is it the same? Is it the same? It is indeed. They're in phase, that's what, there's no, how would you, Eli the Iceman, so for a resistor, I got E and I together. And Eli the Iceman. That's what worked. So the voltage, sorry, the current phasor for the resistor is in phase with it, so boom. Now, I don't know which one is supposed to be larger, I didn't give you enough information, but that does not matter a whole lot. And so now, we add. Despite the way I've drawn it, that should be a rectangle, where this side is I sub R and this side is I sub C. So phasor for the power supply is right there. All right. So let's go ahead and find the impedance, because what the heck? really that's often the problem here. So I know that current for the power supply squared equals the current from the capacitor squared plus the current from the resistance squared. And I know that because I got a right triangle right here and I just did Pythagorean theorem. I know that there's Ohm's laws variations for each of these, that this I, because I know that V equals IR. I know the voltage across the capacitor is equal to the current across the capacitor times the capacitive reactance. And I know that the maximum voltage, or the amplitude of the voltage for the power supply is equal to the current coming out of the power supply times the impedance. So therefore, this is epsilon sub naught over Z squared is equal to V sub R over R squared plus V sub C over X sub C squared.
Now, never mind. I got it.
Okay. Well, I know that all the voltages are the same. We've already established that. Emphasized in the diagram there by the fact that I wrote equal signs in between them. So those would all cancel out. So I'm left with 1 over Z squared is 1 over R squared plus 1 over X sub C squared. I forget I'm solving for C. I'm sorry, solving for Z. Or for the Europhiles, Z. So Z squared is equal to 1 over R squared plus 1 over X sub C squared to the -1. And therefore Z, the impedance, is 1 over the square root of 1 over R squared plus 1 over X sub C squared. And we can take it one step further because there's a formula for X sub C. R squared plus 1 over omega C squared. Please note, this is not the same formula as we had before because, well, it's a different circuit.
What is the C?
It's the impedance.
The C.
Oh, sorry,
By
C,
the omega.
that is the capacitance.
Okay.
So that's omega C squared.
Yes, because the capacitive reactance, X sub C, is equal to omega times C.
Oh, so if we knew the capacitor and the resistor, we could just solve?
Yes.
Just plug and chug?
Yep. So if, what were the numbers I used last time?
60 for the resistor and 30 microfarads for the capacitor.
So therefore, my capacitive reactance is going to be omega times this, and our omega was 314.1592 radians per second. Times 3 times 10 to the -5th farads. So what is the capacitive reactance?
.0094.
0.0094.
Yeah.
Ah, okay. And what is, units?
Farads, or is it farads?
It's not ohms. That is. If you'd said farads per second, that would work. Something's not right. Or did I change? Did I start out with 30 microfarads and change it?
Last time? No, you kept.
I kept micro. All right. Well, let's change it here.
I don't know. I just put it in the calculator, I got 0.09708.
0.0.
0.0978, yeah.
You're just trying to start fights with everyone, aren't you?
Hamster.
Anyone have get either of these values? Or do we have a third one? Did you get a third one, Michael? All right, so let's do it the old-fashioned way. So I got 3 times 3. Yeah, so 314 times 3 gives us a 2, 3, compared to 1, 4, 9, so 9, 4 makes sense. And then I have, times 10 to the negative third, this one actually makes more sense. So let's make it
I think you did change it. Now that I'm thinking about it, because I think we ran into the same issue that you didn't like the number.
yeah, one of them going out to be roughly the same. So if I did,
On here you have the x of c equals 1 over omega c.